Great. Yeah, good afternoon again. My presentation is called Real-Time Wildlife Monitoring, and I'm going to talk to you about the development of an AI-based alert system for reducing human-wildlife conflict in Romania's Carpathian Mountains. So, starting big picture, human-wildlife conflict is broadly defined as any interaction between humans and wildlife that results in negative consequences. So here we have some examples of these consequences. So on the left, we can see elephant damage to houses in India. And then on the right, we can see tourist interaction with elk in the Grand Canyon National Park. We've got an elephant destroying crops, and then livestock killed by predators in Africa. And the key point is that these are becoming more frequent due to population growth, shifting land use patterns, and climate change. And so this is happening globally, including closer to home here in Europe. So Romania hosts some of Europe's largest population of wolves, lynx, bears, and wild boars. Now, all of these species are related to human-wildlife conflict in some way, but this research is going to focus on bears and wild boars, which are of particular concern to some rural communities in Romania. So specifically, bears and wild boars can destroy grasslands, crops, livestock, and fences. And I want to draw your attention to the sort of sequence of images on the left, where you can see, so boars, what they do is they burrow for food under the ground. And you can see how they use their noses to really sort of dig up the grassland, and this can destroy an entire field in one night, which is real concern to sort of livestock owners in many areas. I didn't have any photos of bears destroying crops or sort of infrastructure, but I did capture this sequence of images a couple of weeks ago, and I thought it sort of demonstrated just how powerful these animals are, how much of a threat they can cause to local people. So I was saying that the Carpathian Mountains MCC, they have offices up here in Ruka, and then they deploy 3 rapid intervention teams to the villages in the surrounding area who, notified in time, can arrive at the instance of a bear or wild boar incurring into the village and chase them away. However, as you can see, they have to cover a wide area and they're often not notified in time, so sometimes a day after or a couple of days later. And this heat map shows instances of human-wildlife conflict in that area in the past 5 years. And I think underpins the main motivation for this research. So basically, an automated alert system would enable the rapid intervention teams to respond to wildlife incursions more quickly, helping them scale their work and further improve relations with communities. And so this is that's the overarching goal, and this is sort of how we're going to get there. So we've got, at a high level, a 4G camera trap, which you can see on the left. This is triggered by motion. It takes then a sequence of images, which are then emailed to a server, which runs as a machine learning pipeline to classify the animals, and it's an instant message alert to the rapid intervention team. And I should highlight at this point that sort of one of the key enablers of this is that FCC has 6 years of camera trap data that was used to sort of train a machine learning pipeline. So to achieve this goal, we've got 3 research objectives I'm going to talk through. First is the collection of data. So FCC's camera data, preparing it for integration to machine learning pipeline. Second is then developing models to identify wild boar and bears. And then third is integrating this pipeline into an alerts system. But before I talk through those, I want to just give a brief background to some of the machine learning analysis or machine learning techniques that I'm going to talk about in terms of sort of analyzing camera trap photos. So this research is going to use the 2-stage detection classification approach that was first proposed by Sarah Berry and Dan Morris back in 2019. And the core of this approach is that we will have a generalized detection model and then a specialized species classification model. So the key models I'm going to refer to are YOLO, you only look once, which is a object detection model, Mega Detector, which is based on YOLO but trained specifically for camera trap images, and then the Deep Fawn Initiative, which is a 2-stage open source pipeline which has its own YOLO-based object detection model, and then a vision transformer species classification model. And the Deep Fawn pipeline was considered the state of the art for this research, and the baseline for which further improvements were made. So first objective, was data collection and processing, which included a field trip to Romania. So at the beginning of the project, in sort of around mid-April, I traveled to Romania for a week to collect camera trap data, so it was about 2 terabytes worth, but also to understand the context and to survey potential sites for a field deployment. So we visited three villages. First was Valea Maracavat, which you can see here. So just north of the village, we had grazing land, which had been damaged due to sort of wild boars sort of digging up, looking for tubers. And this was causing real concern for the local villagers who owned livestock, and this was undermining that. Now, the issue with this site, however, big open landscape, where do you place the cameras if you're going to try and detect an incursion? Second, we visit Buka. So similar issue, but for different reasons. So here you have a village nested in a narrow valley with the trees coming right up to the village lines. In this dense woodland, again, made it quite difficult to predict where the animals were going to enter into the village. They could come from any direction. And then the third village we visited was called Lereshti. And the interesting thing about this location is that we had well-maintained fences, which creates some natural passages for bears and wild boars to enter into the villages to get access to the orchards and croplands in there. So we thought, well, this would be a great location for an initial deployment because we'd be able to predict where the animals are going to come from. Now on to the data. I collected about 350,000 photos and videos, of which we had 19,000 labels. Now, unfortunately, we had a big Excel table of 19,000 labels, but none of these records were linked to an actual file. So what we had to do is, well, fortunately, we did have some date and time information, so we could use that and then extract the metadata from the entire 350,000 images and then match them and match up the labels with the files. This worked to an extent and managed to match about 8,500 photos, just focused on photos. But fortunately, because cameras take a sequence of images, or camera traps take a sequence of images, not just one, that was achieved and augment that up to about 90,500 labeled photos. Now, volunteers, these labels were created by volunteers. Research suggests that volunteers have accuracy around about 97%. So to create a ground truth, what I did is I ran the Deep Fawn Initiative's pipeline on this entire data set. I got those labels, compared them with the volunteers' labels. Where they agreed, I said, okay, that's the ground truth. Where they didn't agree, for about 2,000 images, I created a tool and went through one by one, labeling the images myself. Now, that wasn't the most exciting Tuesday night, but it did enable me to produce this table, which is really useful. So maybe I should start, just for those of you who don't know, precision we call F1 scores. Precision, if my model labels 100 images as a bear, but 90 of them are bears, so that's 90% precision. If I have 90 images of bears and my model identifies, 100 images of bears, and my model identifies 90 of them, then it's 90% recall. And then the F1 score is the harmonic mean between the two. And what you can see here is that Deep Fawn is doing very well out of the box, particularly on the two species that we care about. So you've got over 0.95 precision and recall on bear and wild boar. And broadly, we see sort of FCC tends to have better recall, whereas Deep Fawn tends to have better precision. So what are the implications of this? Well, Deep Fawn's already doing pretty well. We'll probably have sufficient data just to do some incremental fine tuning to this. If I was seeing, 60%, 70% precision recall, maybe I would go back to the data and try and get more data out because it'd be more of a training task. But with the starting on here, actually, maybe let's just try and get a pipeline working and see where we go from there. In terms of the modeling objective, FCC had asked, they wanted us to maximize recall. So that is to minimize false negatives. So what we decided is that, what we're trying to do is get the model to perform as well as the human labelers on bear and boar. So that's a 2.2% increase in recall accuracy. So how do we go about this? Computer matrices are really useful to work out where the errors are happening. So just a quick overview. So on the left, sorry, on the y-axis, you've got the ground truth, and then on the x-axis, you've got what the model predicts, and you kind of want to see this final line across the certain models generally getting the labels correct. But if you look at the other entries in those rows, you can see where the errors are happening. So if we zoom in to wild boar, what we see is, yes, it gets 95.3% of the labels correct, but in 2.2% of cases, it's leaving the images as empty, which suggests an error or a sort of failure in the detection model. And in another 2.3% of cases, it's classifying the images as unknown, which suggests a failure in the classification model, which is great because that provides us with a very sort of clear pathway forwards. We should look at the detection model. My approach is to replace the default detection model with meta detector, see if that has an improvement. And then we can improve the classification model, and my approach there was fine-tuning using FCC's dataset. So, which means subjective testing and training new models. So first focusing on the detection stage of the pipeline, like I said, I wanted to see if mega detector could improve deep forms detection model. Now, firstly, I wanted to run both mega detector and deep forms model on FCC's entire sort of 19,000 image data set. However, this was clearly biased towards non-empty photos. So people don't tend to label empty camera trap photos. So I need to balance this out to be able to get an idea of what position to recall. Actually quite a difficult task to find empty camera trap photos that have been labeled accurately, but I managed to find a good quality data set from a mountainous region in Idaho, USA, which may be similar to sort of the Carpathian Mountains sort of landscape. So augmented that, so 19,000, about 38,000 images. Ran both mega detector and deep form on all of these images with no confidence threshold. So again, a bit more background. These models output a confidence level of each of their detections from 0 to 1. I ran the models with no confidence threshold so I could get every detection I could come up with, and then I retrospectively applied confidence thresholds from 0.01 up to 0.98 to be able to work out what the precision, recall, and F1 scores would have been for all of those different thresholds, which then enables you to create this sort of precision recall curve. And this sort of shows that there is a trade-off. All models exhibit a trade-off between precision recall, but the deep form model here manages this trade-off better. So the mega detector model manages this trade-off better than deep form. So you have a given recall target, say 0.98, you will get higher precision always with mega detector, which provides us the evidence that switching to mega detector on this data set would likely bring positive results. Now moving on to fine-tuning the classifier. I needed cropped images to fine-tune the classifier. So I ran mega detector on the data set, and you end up with these types of crops. So this is an example of the varying quality of images that we're dealing with here. Then go relatively conservative fine-tuning approach. So freezing majority of the layers at relatively low learning rates, and created a custom loss function, experimented with custom loss function to sort of penalize poor performance specifically on boars and bears. And then experimented with a range of different models, but dove a bit more deeply into two types. One was balance loss model, so just normal cross-entropy loss, and was bias loss model with the sort of penalty weight set to 10. Ran both for 30 epochs and sets the best epoch based on the maximum harmonic mean of bear and wild boar recall, which is it's a custom metric as opposed to just looking at loss. We cared a lot most about recalls, and we focus on that. And I think these graphs here, because I thought it's quite interesting, you can actually see that the training and validation loss diverge quite quickly during training, but the harmonic mean of recall continues to increase, which is what we cared about. And so we go to the results, actually seem to pay off. So the bias loss model improves bear and wild boar recall by sort of 4.4, 3.3% respectively over the default model. And then the balance loss model will perform best across all classes, looking at both precision recall and F1. Great. So now I had a new detection and classification pipeline. I need to integrate this into an alert system for testing in the field. So this video will demonstrate how the machine learning pipeline was integrated into the alert system. On the left, we've got the script that sort of regularly checks emails for emails arriving from the 4G campus. And then on the right, you've got a mobile phone that's where the alerts will be sent to. I'm going to simulate a email arriving. We will see the system receive this email, extract data, negative data there on and detect the animals. Then we'll the visual transformer classifying each species. And then it will generate an alert, which will then send to the mobile phone on the right. Then the rangers can receive this alert, they can click on it, they can scroll down and look more information, so where it's located, what time, you can zoom into the images. Manual inspections is quite important just to make sure that there's no mistakes in classification. And then there's the things like you've got the map link there, so you can open it up in your Maps app and navigate to where this particular detection took place. Maybe we could just draw your attention back to the left-hand side of the screen. You can see there it says no human warning, sending photos regardless of time. So one thing we found is that during the initial testing, we were starting to get lots of photos of people, which raised obviously certain issues around privacy and sort of sort of data protection laws. So what we did is we decided to, well, in the mega detector stage, if it detects any people at all, it sets sort of, in any of the 5 photos that it receives, it sets a sort of human warning flag to true, and then the system won't send any photos if that's detected. We've actually set this during daylight hours for now because FCC requested that we still send photos to people during nighttime because it will help their anti-poaching law, anti-poaching work, which they are sort of legally sort of enabled to do. Also, one final point. While relatively trivial from a technical point of view, we translated the messages into Romanian, which is of course very important for the uptake of the system because the rangers don't necessarily speak English, so this helps them understand what's going on. In terms of the deployments, we started with an initial deployment about 2 months ago now, at a feeding site just to maximize detections to sort of refine the system and develop what we've just seen. And then we deployed the system live with some rangers in the group at 2 locations just north of the village called Alberti. Now, I didn't actually visit this village during the field visit, but the rangers have requested this because there's been an increase in sort of incursions in this area. So in terms of the performance of the system, I evaluated the new pipeline on the 21st of June, so a couple of weeks ago. It had processed 1,135 photos in 39 days, and this was within 328 detection events. So remember that each event can result in multiple photos. I'm pleased to say that the recall objectives set out at the beginning of the research were achieved for bears and wild boar. So we received 97.6%, 97.8% recall on the photos. And obviously, I appreciate this is a relatively small sample size and be interested to keep monitoring this over the next few months. But obviously, these numbers, while important, don't matter if you're not having conservation impact. So I also held a structured interview with the head ranger, who was part of this Telegram group, and just to get his feedback on how the system was helping him with his conservation and sort of deterrent work. He reported that about 3 to 4 incursions had been responded to as a result of this system, and that he appreciated the fact that he was getting these reports much quicker than speaking to farmers. He also noted that it was really helpful to have all of this information in one group so that whoever's working that night can see what's going on with the image data. One piece of feedback he did give is that the system does tend to make a few mistakes, also give some confusing alerts when you have lots of animals in one photo, which is something I'll talk about in the discussion now. So, achieve the 3 research goals, but there are obviously quite a few areas of further work. First is on the data. So you have 250,000 images, but only ended up using about 8,500 of them. Now we could easily double this by using videos as well. I've got labels for some videos. I could extract, 5 or so frames from the video and I could double it. I could probably double, triple it again by using some traditional data augmentation techniques, horizontal flips, contrast adjustments, and etc. And then you could look at sort of semi-supervised learning approaches as well. So sort of creating pseudo labels out of the highest confidence um, detections and adding in sort of real ground truth with pseudo labels into each batch to sort of further augment the data set. In terms of modeling, I think there's probably diminishing returns to improving the detector model. However, mega detector is currently maintained by Microsoft. They've introduced a newer version that's going to be released in the next few months or so. So perhaps just swapping out with that could come some quick results. Hyperparameter tuning, there's quite a big hyperparameter space. I didn't have time to implement sort of one of those sort of frameworks like Optuna that you could use to explore that more efficiently, but potentially you could get incremental improvements there. But I think the key point to make is that actually the biggest areas of improvement lie outside of training more machine learning models, but instead just making better use of the data that we already have. So, like I mentioned, I think more work could be done on sort of coming from more sophisticated algorithm for generating the alerts. At the moment, I just give an alert based on the highest number of animals detected in the 5 sequences. But what I could do is maybe look at the top 3 detections for each animal in each photo and come up with a sort of smarter way of thinking. Well, animals don't tend to mix, so if I've got 12 wild boar detections and 1 cow, like you might have seen in the processing there, then I'll just say label them all as well, to avoid that kind of confusing alert message. Another thing we found, which we can talk about more if interested, that we actually put 2 camera trap brands on at the same location to test their relative sensitivity. And what we found is that the overlap in detections was around about 60 to 70%. So actually, the recall was being significantly affected by the hardware as well. So that's something that I think needs a bit more work to work out, okay, which camera brands are better for which objects, because one camera seems to be better at smaller objects, whereas the other seems to be better at larger cameras. And then finally, recall versus credibility. So FCC requested that we maximize recall. And that's what we did. We lowered the confidence thresholds and maximized recall. But actually, when I got feedback, they said, well, it gave some sort of weird results. It identified a dog as an ibex or, a wild boar as a bear, etc. And actually, there is a balancing act. It's a bit more sort of qualitative in these kind of systems of thinking, okay, well, you've got to maintain the credibility because people don't understand what's happening in the background. So the system has to be credible. And if it gives a ridiculous, prediction like a dog is an ibex, then it could undermine people's trust in the system and make them use it less. Where actually, if I increase the confidence threshold, maybe we do miss a few wild boar, but people trust the system more and use it more in their day to day. So we're planning to hold a workshop over the summer at some point with some of the rangers to get more feedback on the system, and perhaps we can make a few adjustments there. So final slide. Yeah, so basically, just a couple of points that I thought was quite interesting. So firstly, the first thing is I'm aware of, and if you're aware of others, do let me know, that uses remote processing of 4G camera traps to operate a human wildlife alert system. So there are some systems that do on-device processing and then send alerts over the satellite network, and that's, I believe, largely of a lot of human wildlife conflicts happening in areas that's very remote and don't have mobile network. But as mobile network expands, including in some of these areas, I think this research could have broader applicability in the coming years. And second, this is the first study that I'm aware of that looks at all stages of the alert system development. So you've got the sort of the machine learning side, the data collection, the model training, etc., but then also the field development and conservation impact side of things. And I just want to highlight that this really does come down to FCC and how quickly they were able to deploy the camera traps, and then their strong engagement throughout, which really helps them focus where the software development work and sort of work out, okay, where do I work to have the biggest impact on what they're trying to do. So just a big thanks to them for their support with that. So that's all from me. Thank you very much, and take any questions.
Okay, we have plenty of time for questions. Anybody in the room? Oh, you're going to keep, okay. So if you're online, you want to ask a question, please just unmute yourself and ask.
I have a question.
Oh,
If there's something live.
yeah.
How did you assemble the system on the server to do process the email and do this analysis on it and then send out the WhatsApp message? How did that work?
Yes. So initially it was running on a Raspberry Pi for about a month. But then we wanted obviously a more long-term solution. We set up a virtual machine on FTC servers. They've got their own servers in Brasov in Romania. So we set up a virtual machine, so working with their security company to make sure it was also set up securely. And then yeah, there's just a script that's then running on it connected through SSH. It's I think it's we've got 2 GHz cores, 8 GB of RAM, and it can process an alert in about a minute, which is sufficient. It probably could reduce the number of cores. It would take a bit longer, but at the moment they're happy with the amount of resources taken on this server. Yeah, I think areas that we could make it more robust would be first, we're relying on Gmail for the emails. I think it would be neater to, instead of the camera trap sending an email to Gmail, for it to send the email directly to the server. So if we were to set up sort of an SMTP server on that server, then we sort of cut that sort of area of uncertainty. I suppose as well, we are reliant on Telegram's API. You could do this on WhatsApp as well, but WhatsApp charged to use their APIs. That's why I use Telegram. But yeah, that's working. Cool.
Thanks. I think just to kind of this spatial naming system kind of ideas would be very relevant here because right now these biodiversity traps are camera traps are just they just I mean you can see Tom has a model on his desk in a small box, but they are on the cell phone network. I think you might want that. But if you go after that, you get nothing. Right?
Yeah.
You go out there and they get nothing. And what spatial naming system can do possibly is to have local distribution of names, all the stuff you've been working on. So that the rangers can get data from that trap, I'm going to look at it right now, we don't have access to the trap data, other than, what Tom has done to access, format it, etc., and send an alert. So that works, but then I think what you can do, there is actually a possibility for what you can work on to bring it back from package management to the spatial naming system.
Yeah.
Possibly, but you should talk to Tom about that.
Yeah.
It'd be good to, yeah.
Yeah, so go ahead. Stefan has a call question, so please go ahead and unmute yourself.
Thank you, Tom. Thank you for such a great presentation. I do have a question about how you did the evaluation in terms of splitting the data into train, validation, I guess, testing. Did you train and test on the same camera trap locations, or did you have camera trap locations that you kept specifically for testing?
I don't have a grasp of the locations, but I do have this. So yeah, I did think about how to split up the train test validation sets. Also the day-night quality species occurrence, but also looked at location. So there were about several dozen different locations. I've got probably about 50 to 60. No one location had more than 10% of all existing, all of the wild boar or bear photos. There were about 5 or so locations for both bears and wild boars that had only captured bears and wild boars. But there were a couple of images at each, so I didn't think that was going to have a huge impact on, sort of what's it called, shortcut learning, where the model learns the particular angle or particular type of camera would equals bear or wild boar. The one area where I did have to make an adjustment was on sequence of images. So, like I mentioned, you tend to get a burst of images of the same panel. I wanted to make sure that that was split across training, test, and validation sets. So I sort of grouped by sequence and then split between the two. Does that answer the question?
Yes, I mean, my main curiosity would be whether any of your model would be tempted to learn specific background of the camera trap, because I suppose you don't move the camera trap. Like the angle stays the same, so maybe the model could learn the same rocks or like leaves and kind of understand that in this location, maybe boar is more common than any other species. But yeah, like if you have the limitation of not having enough images, then yeah, I understand it's a difficult decision. Thank you.
There are two questions from Brent. Brent, do you want to just unmute yourself and ask them?
Sure, yeah. I hope you can hear me. I guess my two questions are quite different. The first one is sort of how quickly could this be set up in a completely novel situation where you don't have a large amount of data? And then the second question is whether there would be a use. As far as I could tell, there wasn't a stage at the end where the photo that triggered the alert was then reviewed by the rangers, and I wondered if that would be a useful final step in the process to sort of have another chance to identify errors. Those are the two questions, and whether, yeah.
Yes. On the first question, I think it would depend if there's a pre-trained model that exists or not for the species of interest in the area that you're setting up in. In terms of if you're looking at so European mammals, there's the Deep Fauna Initiative. There is another model that's not peer reviewed as far as I'm aware, but it's relatively easy to swap in a pre-trained model into this pipeline, and you could get it working within a couple of days. If you're looking at species that really there's no model for, then that could be quite tricky. Yeah, I think I imagine a lot of the animals that sort of people would want to monitor for in these sort of human wildlife alert systems, there are large data sets for, particularly sort of African and North American animals. That's where I found most of the classification models, and there's quite a lot of options there we could use, and it's quite easy to then just sort of swap in that model there. I mean, the model that I've already got running on this, it already works on 26 European mammals, so if it's in Europe, there's a good chance that the animals that you care about would already be there. I should also add actually that there is a GitHub repository, and I can share a link with anyone that's interested, but it has been designed in a way that it should be somewhat relatively, I mean, my level of Python skills is relatively introductory and can sort of get it up and running on their system. In terms of the rangers reviewing the photos, so yeah, I mean, so what happens is, I know we've got 7 people on this WhatsApp group. I think there's about 20 or so rangers, and yeah, the idea is that they will all join the Telegram group. And yes, they review the photo, they get the photos themselves, and then they will review it themselves before deciding on whether to intervene. And maybe they'll look at what direction the animal's going in, or if it's a bear, it looks like it's a large male, or you know, they'll make those sort of human judgment calls before reacting. If you're talking about sort of the system receiving and processing the image and then sending alerts, there's no human in between that bit. The alerts just get sent out automatically. Did that answer your question?
Yeah, that's great. Thank you very much.
I'm curious if you have a sense what the needed camera trap infrastructure needs to look like for this sort of system to be effective. Like for this to be deployed in a new area, like how many camera traps need to be region, this sort of question.
Yeah, it's a good question. I think to be honest, I don't know. I was trying to find some information on sort of how you might take a more mathematical or strategic approach to sort of deploying camera traps in an area like some of the villages that I showed before, where you've got open grassland or just dense woodland, you don't know where they're going to come from. I think is largely going to come from the rangers themselves, and they'll just have a sense of, oh, they tend to come from here, and so we should put one here. And perhaps starting with the low-hanging fruit to build trust in the system. So, for example, the location that we selected in El Pashti was again on 2 footpaths, and they were used by humans and wildlife. So that was kind of an obvious place. It would be great if we could get some more set up in the Esti, where I showed the photos of the fences. Because again, that would help build the trust in the system. But I think it's start with low-hanging fruits and then experiment with the more difficult locations, which but yeah. But if anyone on the line has ideas on how to do this on camera trap deployment strategies, it'd be good to see it.
I think it's a difficult question. It really depends on what the camera traps are there for. Human wildlife conflict is just one type of thing you could use traps for. The other one is biodiversity monitoring, and you do different things. I was recently talking to one of Andrew Bumpert's postdoc students, and what they're doing using camera traps for a completely different reason, which is to see how many humans go past a particular segment of the trails of women in Western Canada. And they wanted to see the impact on the wildlife. So they measuring both humans, are they on horseback or walking or bicycling, versus the same region, what animals you see. So again, what it does be very different. You're going to along the trails most likely in some interior region. So depending on the use that you're going to put it for, I think you have very different coverage results. Yeah, but I think the one takeaway that I got was that putting together the whole system is a lot more than tuning the AI. They're tuning the AI, which is sort of what we focus on mostly in research papers, was perhaps the easiest bit in some sense. The data preparation was pain.
Yeah.
It was just very difficult to deal with 6 or 7 different data types and very different ways of labeling the same thing, and that took you a very long time. And then putting the system together, I think getting the virtual machine configuration properly set up, understanding what to do, and so on was also not obvious. It's not. There's a lot of little bits and pieces that don't all necessarily work, and it's what was remarkable was how quickly it came together. I think in part because Tom is very meticulous and very good about documenting stuff, but also because our partnership with the FCC was brilliant. I mean, we asked them to set up a trap, as crossing the fingers to see how long it would take. It in 2 days. They just did it. It was amazing. And then we said we'd make a virtual machine, and a few days later we had one. So it's just been probably one of the best experiences I had in getting with real partnership with this guy. So I think a lot of the credit goes to them as well in being really supportive and giving access to 2 terabytes of data random from it. I think fantastic as well. So yeah, I think a great result, but really good collaboration as well.
Yeah.
Any other questions on that? Or actually here? Okay, in that case, thanks, Tom. Stop the recording here and
communities.